Alright, here we go. The audio quality might be a bit iffy this time, but it'll be tolerable. So, let's get on with energy. Now, of course, we always have our little disclaimer that you need to know Newton's first, second, and third laws, vectors, and trigonometry before diving into energy. You don't have to be masters at them, but they will help you understand different concepts within energy. Alright. Okay, as always, I'm Alex, and Esther is the one with all the practice problems, so thank you for that. And we'll start with our table of contents. First up, we're going to go through work and power, and specifically the work-energy principle, and then we're going to go on with mechanical energy, going with Hooke's law, EK and EP, in regards to springs. Then we go on to energy systems, which is the law of conservation of energy, one of the most important laws you will need to know for AP Physics 1. Of course, practice problems as we go. Okay, let's get started. Work and power. We have our concepts here: force, displacement, and energy. Force, we know from dynamics, and we know it's in joules, which is also the same as Newton meters. Displacement, we always go with meters, and energy, of course, is in joules. Now, work and energy, we have two general formulas. So work equals force times distance, or the change in energy. And the next one is work equals force times distance at an angle, and we use cosine theta for that. So let me highlight these two. And what you can see is that work and energy, they're single variables, which means they are interchangeable. So let's say interchangeable, meaning they both equal force times distance, and it's just a matter of the language that the question uses. We know that work and energy, because it is a force over a distance, work and energy, or change in energy, they are scalar quantities, not vector quantities, scalar quantities. Perfect. Now, net work, which you can see as W net, means a constant period of time, so work done over a constant period of time. And that's why you don't see time in this formula here. So work done over a constant period of time. And we know that the most basic kinematics formula, if we're going to isolate it for distance, d equals tv, that because it's a work over a constant period of time, the velocity must change according to the distance. D and v are a 1-to-1 ratio, because essentially then d, the first formula we have here, work equals force times distance, is only for linear movements. And by linear, I mean not at an angle. So what happens if we approach something with an angle? Well, then we would use the second formula here, work equals force times distance at cosine theta. Now, the easiest way to think about this and to conceptualize it is when perhaps we have a wagon. Now, we'll draw it like this. This is our mass free body diagram, pulling at it at an angle. So if the blue line here, if we were to pull with the blue line, we would use work equals FD. If we were to pull with the green line, we would have to use work equals FD cos theta, and theta will be the angle here. So if we take a look at this, perhaps on our Cartesian plane, we always have this x-axis here that would be W equals FD. And whenever we go at an angle, anything in this area, this region, less than 90 degrees. So we look at here, if theta is less than 90 degrees, then it's positive for the value. And if we have in any of these areas here where theta would be negative if it were to be more than 90 degrees. And then if we had just straight 90 degrees, we would simply be pulling up, and that would still be a linear motion. So we would still use work equals Fd. All right, awesome. Let's go on to the next section. Power. Power, as you can see here, is the change in energy over time. And because we know that energy is basically work, the change in energy relates to work, then we can write it as work over time as well. And we measure this in watts. So if you think to your light bulbs, this would be the power or the work and energy change over time. So there's really nothing else to it right here. We have power equals E over T, power equals work over T. Change it around. There's only 3 variables, so nothing should be too difficult. And of course, you can always substitute this as Fd over T, or with the other formula, Fd cosine theta over T. Oops, sorry about that. Over T. Now, before I forget, there's actually another formula for work that we can work with. See what I did there? Work equals mgh is also a formula that we have. I forgot to list it up there, my apologies. Work equals mass times gravity times the height. And this will be used in our next problem, which we'll get to right now. So if we have this problem here, 75.6 kilogram athlete running up at a constant velocity on a 21-degree incline, producing 3.1 kilowatts of power while running 34.5 meters up the incline, and determine the time required. So I listed our known variables on the side, and be sure to write kilowatts as watts. Don't mess up your digits here. As always with any physics question, we should start with a free body diagram. It's a great habit to build. So if we have this ramp and we have 21 degrees as our incline, we have 34.5 meters. We have a height right here. So we know our formulas that we're going to use. Because we need time, we can use the time power work formula, which is P equals W over T. And we know the W from 2 seconds ago is mgh. So here we just need to isolate. And we know T was equal to work over power. And we have our power. We have our power variable. Now for work, we need to calculate. We have our mass, and gravity we're going to use 9.81 meters per second squared, but of course you can always use 10 meters per second squared. It depends on what your teacher teaches you. On the AP test, it does not matter whether you use 9.81 or if you use 10, as long as you write it down on the paper stating which value you're using. So we have our mass. We have our gravity, and right now we need the height. The height we can use with simple trigonometry. So if we think of SOHCAHTOA, and hopefully you've learned this trick by now, we can say that sine 21 equals h over 34.5. And let me move this down here. Which means sine 21 multiplied by 34.5 would give us h. And if we do that real quick on our calculator, make sure your calculator is in degree mode if you're using a graphing calculator, we would get a height of roughly 12.36 meters. Don't keep the value in your calculator, don't round it. So plug that into here. Let's times it out on our calculator. So if we take our height, we multiply it by 9.81, and we multiply it by 75.6, we get a work of 9,169 ... different decimal places here. Plug the work into this formula here, and we're going to divide it by 31,000. Then we get a time of approximately 2.95 seconds, and actually it should round to 2.96 seconds. We see here, however, in this question, we have significant figures, and our lowest significant figure are two figures here for the 3.1 kilowatts. So the final answer equals 3.0, or just 3 seconds. 3 seconds, basically. But if you wrote this on the test, they really can't mark you wrong. You did your work properly. So on the AP test, it's okay if you mess up on your sig digs, as long as it's not too significant, because ours is valid here, so there's 3 sig digs here and 3 sig digs here. Alright, moving on to mechanical energy. Kinetic and potential energy, you'll be working with them quite a lot, and they are the fundamental energies that you'll need to learn. So you can see here that EK, kinetic, equals 1/2 mass times velocity squared. And EP, potential, let me write that here, potential, is the same as MGH. And if you take a look, MGH, we had our formula back here that work equaled MGH. So in reality, when we used it on this ramp here, the reason we used work equals MGH is because at this top point where he stops, he is actually purely focused on potential energy. Now, potential energy, what it is, well, for lack of a better term, the potential to have energy. That's not helpful at all. I know. This will make it helpful though. Let's say we have a wall. That was a terrible wall. Anyways, and we have a ball on top of it. When the ball is sitting on the wall, which rhymes, I didn't mean it to, but it rhymes. The ball is sitting on the wall. It's not moving, it's stagnant. And what happens is gravity is acting upon it, right? And here we have a natural force holding it up. But of course, we're focused on the gravity. We're not really focused on the natural force. We're focused on the gravity and the potentials of that gravity. Because as soon as this ball falls off, let's say it's here now, there's no natural force to hold it up. And so gravity will work upon it and make it fall. And as it's falling, it turns into kinetic energy. So potential energy is going from a state of no energy into a state of kinetic energy. And that's the conceptual theory behind it. Now, of course, we know that we have our own formula, EP equals MGH. And I just explained kinetic energy. Basically, it's when your object is moving, and you can see that with the velocity squared right there. So, pretty intuitive. Let's see how to apply these. And before I move on, Remember we said work equals change in energy. Specifically, it means the net work equals the change in kinetic energy, because when you have potential energy, you're sitting in one place. You're not really changing. And of course, there will be changes. We'll look at those later, but that doesn't relate to the W net equation. Elastic spring potential, and we write that as EP. Of course, some people might write it as ES for spring. I will just be denoting it as EP because it is still a type of potential energy. Now, what helps us here with the potential energy of a spring is Hooke's law. And Hooke's law is this section here. Hooke's law is force equals negative kx. You're like, okay, what's k? K is a spring constant. Spring constant. And it varies from spring to spring. It varies based on the material the spring is made of and how the spring reacts itself. So it's unique to every spring, and it is a constant value. When using Hooke's law, we can derive a potential energy formula, which is 1/2 kx squared. So what is x? You might say x is the displacement of the spring. There we go. When we say displacement of the spring, we mean the free end of the spring. So we have some springs, and let's say our first spring, we'll make these horizontal on the ground. So this is a wall, and we have a spring attached. Let's say the spring here is in its natural state, okay? Nothing's happening, no one's touched it yet. When we say displacement of the spring, we are referring to the free end of the spring. So if we were to stretch the spring, like so, with the free end here, then the x value would be from here to here. So that would be our x value, is the change in the distance. And same if we were to perhaps compress the spring. So we compressed it. Then the change in distance, let me change the color, then the change in distance would be from here to here. Now, you will have positive and negative values, of course, but it's different for each question if they don't state it. So I can say that this is a negative compression, and I can say this is a positive extension. But of course, these vary problem to problem. Maybe it'll tell you that a compression is positive or an extension is negative. It really depends. Now, don't focus on this, because we have, if you see this, we have a negative k, and what we do is we don't really use the negative. The negative is there because the restoring force is always in the opposite direction of the displacement. If you think of a spring, the restoring force, let me write that down actually. Restoring force, I'll let you take a guess what that is always opposite of the displacement. Because if we have a spring and we stretch it out, we stretch it to here, the spring is naturally going to want to bounce back. And if we compress a spring to here, the spring will naturally want to bounce out, and not as exaggerated as that, bounce out to its normal form. So restoring force is always opposite of the displacement. Our displacement is mostly positive, and so they put our restoring force as a negative just to show the vectorized placements. But when we use it, we just use F equals kx. Basically, we just neglect the negative. You'll see this commonly on questions as well, so don't worry about positives or negatives for these types of questions. Because all in all, we're going with force and energy. You can't have a negative force, or you can't have a negative energy. You can have them in different directions relative to each other, which you can label as negative, but there's no such thing as negative force and negative energy because you don't take force, you don't take energy from something. This is not chemistry. Alright, so that is our kx, and then for potential energy, you just square the k and you put a half in it. Let's put it into practice. A spring having a constant of 23.4. Okay, let's go with the practice problem. A spring having a constant of 23.4 Newton meters stretched so that it has 0.335 joules of potential energy. Determine the distance stretched. And this is really easy here because we have potential energy equals 1/2 kx squared, and we just need to plug in our values. So, spring constant, we know that k equals 23.4 Newton meters, and the displacement, the x, is what we're solving for. We know our potential energy equals 0.335 joules, which means we just need to rearrange this formula to solve for x. Remember, not x squared, so let me take this off. And what we'll do is we go EP. Now, whenever we divide by a half, we just times it by 2. So 2EP over k, this all squared rooted equals x. So if we plug in our values in our calculator, I'll write it out here, but I assume you have a calculator in your fast fingers and you're typing it all out right now. Write it out for clarity's sake. And what you should get is x equals, now let's see, we are sig digs, so let's go 3 sig digs equals 0.169 meters, and this is our answer right here. Awesome. Energy systems. This is pretty intuitive. I swear it's not going to take more than 10 minutes. The law of conservation of energy basically states that energy can neither be created nor destroyed. However, it could go through a form shift or phase shift from light to heat. In isolated systems, which means there are no external variables, energy is always conserved. What this means is that the total mechanical energy is the sum of EK and EP in a system and will remain constant in a frictionless system, because we know that friction is a loss of energy. Friction is a force that's acting against, and so it results in a loss of energy and forces. We mostly state this as ET, or people will write just E total equals EK plus EP, and these are also total values. Which means if you're given the E total in a question and perhaps the EK, then you can solve for the EP, and vice versa. It's just a 3-variable formula. For all questions involving energy transformations, you need the first state of energy is conserved. So really, it's a 2-second thing. It takes 2 seconds of your life. You say energy not conserved or conserved. Then you need to state the different types of energy present. Then you need to state the types of energy present, which again, 2 seconds of your life. Just go, there's EK equals something, EP equals maybe you're solving for it, and ET equals something. Now, ET is not an energy in itself, so only state it if you're given it in the question. You just need to state EK and EP. If energy is lost, explain why. And again, this can be due to friction, loss of heat. It can be outside forces. Etc. So again, no extra external variables are allowed if we were to conserve energy. To demonstrate EK, EP, and E total, we're going to label points on this roller coaster track here of points where potential energy is at a maximum and kinetic energy is a maximum, and we're going to assume no friction. No friction. So let's take a look at our points. Our maximum EP is when the height is at a maximum. So if we were to look at the total trail, here is the highest point. This would be our point of EP max. And if we were to look at the lowest point, where we have EK max, we have 1, 2, 3 lowest points where EK is at a maximum. And you could validly argue that only this one point is at an EK max because we start with a higher EP max. So if we're going to compare these points, actually, let's break this down into 3 sections. So let me take my pencil, my highlighter. This is one section. This is another section here. And our last section here. Okay, so we already labeled the blue points here. There's EP max, EK max. In this section here, we have EP max and EK max if we're only looking at this section here. EK max. Okay, and if we look at this loop-de-loop section here, EP max, now if we look at this loop-de-loop section here, EP max would be here, and at the bottom, so not here yet, in this section we're actually here. If you were to look only at the loop, like only this part, yes, it would be here at the bottom of the loop. We're looking at this entire section, so the lowest point is EK max here. And for our last section here, if we were to look at it as a horizontal line, we still have EP and we still have EK, but we wouldn't have a max really, so it would be on the same line. So EP max would be the same as EK max, and then you would go EP plus EK equals E total. That's how it works here. And again, you can just use this and the ET equals EP and EK max formula. Now, this is all pretty logical, right? We know our potential energy. Again, we're on the wall, we're at a height. So if we were to calculate these, we would need to know the heights, or the total energy and the kinetic energy, and we just arrange the formula. So another conceptual problem you'll find and you'll come across especially on AP Physics 1 with energy, is pendulums. And what we're going to do here is label, again, EK max, EP max, really quickly here. So let's say a pendulum is swinging and it goes to A and then B and then C. Okay, so it's swinging this way. At A, if it were to stop, it would be at EP max, because if we look at the center of mass, center of gravity for each, A will be higher. Now C, basically the same as A, but let's just say A is a tiny bit higher than the reference point, which is B. This is the lowest the center of mass can go since this attached to a spring. And because of this height here, EP max would occur at point A or at point C, because essentially we're taking this and we're just mirroring it across B. And B, we would be at EK max, because at the lowest point possible. If we're to graph this for EK, from oscillation as we move from A to B to C, at A, we have no kinetic energy. Okay, we're going to assume that it pauses there for even the slightest of a millisecond. We're going to assume that EP is max at A, which means it starts at 0. And then as soon as it gets to the middle of the oscillation, which is point B, it reaches its max. And then as soon as it goes to point 3, and as soon as it goes to point C, it goes down to the lowest point again. So we would have a curve like this. Same with EP. We know that when we're starting at A, we're starting at maximum, and then we go to EK at B, where EK is max, so EP must be 0. And so we have basically, that is a terribly drawn curve. I can't draw on this. It's just the opposite of EK. We'll look at our total energy over time. We need to compare the points. Well, we have a minimum point and a maximum point, a maximum point and a minimum point, a minimum point and a maximum point. So they all balance each other out, which means our total energy over time is a constant rate. And it does make sense because here we have an isolated system. The pendulum, no friction's acting on it. We don't have any outside forces. So our total energy is constant. That is all for today. That was half an hour, maybe a little bit more than that. But I hope we got the basic concepts across to you for energy. And I hope you understand everything. If you don't, you can always comment below if you have any problems or questions whatsoever. We also put our Instagrams up there in case you do need to contact us. Perhaps send us a picture of a problem you might need help with, and we'll try our best to help. Alright, I'll see you guys in the next video. We're coming with these month to month as we are also students and we need to get our schoolwork done first before we make these for you guys. So apologies for the 1 minute video. So apologies for the 1 video per month basis we're rolling out right now. But I hope you enjoy these, and liking and subscribing will support this channel at no cost to you and will help us continue to make these videos. Okay, see you guys next video.